I'm Jeff McCartney. I want to go over how neural networks work, overview, and then some details. I created a video on natural language processing a couple days ago or whatever, yesterday. It's up there on my YouTube channel. Provide a link. Check that out. This kind of builds on that conversation. So let's get into it. So neural networks are great for pattern matching. So for the example I got on the slide, I just have three blocks, basically a color palette or a color. So we feed that in as a value into the neural network, and then those three colors create a pattern. For our first example, it's red, green, and blue. That specific pattern will be trained to the neural network so that the neural network can recognize that specific pattern and give us a result saying how close the current input to the network matches the trained pattern that's stored in the network. And for the example, we got 97% for the red, green, blue, and then if we feed it red, 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 it'll be a lot lower because we're not looking for that pattern. So we want it to be proportionate. And then, of course, green, same thing. We're not looking for that value, so we want it to be low. That's the high level. So any kind of pattern we can think of, we can store into the neural network, and then it'll be able to give us a percentage comparison to any new inputs that this network sees. So if I were to give it yellow, black, and white, it'll give us a percentage value that may or may not be close to the pattern that we're looking for, which is red, green, blue. And if it's close, then we'll have to go back in and retrain the network and get it to separate out the result to make that yellow, black, and white one more distinct of a result compared to the one we're actually looking for. So we know that it's not actually what we're looking for. So how does this actually work? So when we give it a value, let's say red is 10, green is 5, and blue is 1. And the network has an input layer, which is the first layer of nodes on the graph. And then it has an output layer, which creates the percentage value comparison of what the overall network is looking for. So in our simple example, red is 10. The link has a weight on it as well, which gets applied to the value that's being inputted. So 10 times whatever the weight is, we're going to start with 1. So 10 times 1 is 1, or 10, sorry. And then green is 5. Our weight value is 1, so it's 5. And then our blue value is 1 times 1 is 1. So then we add those values up, so that would be 10, 5, and 1 added together, which is 16. And then we divide it by the number of links connected to that node that we're currently processing, which is the highest node in this case. And so, we divide it by 3. We divide 16 by 3. That's 5 and some change. So that's a decimal point. So it's 5 point, big decimal point. That's our resulting value for red, green, blue. Then if we send it red across all three input nodes, we will end up with, 30? So that's 10. So we have 5 for the color we're looking for, but then we have 10 for a pattern that's not what we're looking for, but it's completely red. So while they're distinct values, they're separate values. We want a percentage comparison, and we want to make sure that they're separated values. So we will go in here and tweak the weights on the links to make sure that the red value is actually below the red, green, blue value, and until we get there. But with this simple implementation of the graph, we can't actually achieve that value. So you need a bigger graph. And that's where an actual neural network comes in. And that's what this view is showing. So we have the input layer at the bottom, and then we have the output layer all the way at the top. The green squares in the middle is what's considered the hidden layer of the graph. And it's hidden because the computer actually generates all these nodes. So you say, I want 5 hidden layers, and the computer will go out and create the each layer with the same number of input nodes, and then link every single combination of the previous layer, which the first layer would be connected to the input layer, and they will create all the possible link combinations between those two sets of nodes. And then it'll go to the next layer and create all those nodes, and then link them to the previous layer, is, you know, all the combinations that exist there. And it does that all the way up to the output layer, or however many hidden layers you requested. So back to our color example, we're looking for 3 values, and we want the red not to be 10. We want it to be less than the pattern that we're looking for, which is red, green, blue. And we get there by increasing the number of layers. So the first time we have 1 layer, and we're not able to change the link weights to get the complete red below the red, green, blue, and so we add another layer, and we do it again. So how do we get the link weights to adjust to make it to where the red value is below the red, green, blue value? How do we do that? And that's they call that back propagation. So we know that the red, green, blue value is our 100%. And so we say the output value at the highest node needs to be 100%, or 1 if we normalize it. We actually get 1. And by saying that, we then perform back propagation, which goes to the first set of links at that top node and adjust those weights to get the second layer of nodes to result in 1. And then it goes to the next layer, adjusting those links to adjust that second layer to be what it needs to be. And it goes down all the way through the graph until it gets back to the input layer. And so you keep doing that, showing it different values. You keep adjusting this, the link weights, to get that separation, to create distinct values for every input that it sees. And when you get to a point where you've massaged the link weights to address each input value that you know of, then you can see if you need more layers if the values are too close. So let's say we've gotten the red, green, blue to be above, so it's at 94%, but the full red one is hovering at 88%. That's still too high, so we might need to increase the number of hidden layers in our graph until those values start to separate enough to say that, you know, a full red is probably 30% accurate compared to our red, green, blue value that we're looking for, and we'll keep separating or adding hidden layers until we get that level of separation. So moving to a more concrete example, let's say we have a scanned in document, either handwritten or typed, and we want to recognize the letters of the alphabet. Well, we need a lot bigger graph than just 3 input nodes. In this case, we'll need 64 input nodes. We're just basing it on a simple 8 by 8 pixel space, nothing too complicated. We can up it if we need to. I was hoping that 64 would fit on the slide, but I got some dots because it doesn't. And then also this graph, I tapered it towards the top, which in reality you wouldn't actually taper, you would keep it squared. Only the top node would be the resulting output. Now you can have graphs with multiple outputs. There's a guy that wrote a paper on that, and I'm not sure of the details on it. I mean, one could assume that you just step down to that first that first layer below the output layer and read those values, and those are distinct enough to say that when you see this pattern, these set of nodes will be a high value. When I see that pattern, those nodes over there will be a high set of value, etc. But I haven't played around with it enough to say exactly how that works. Right now, it's just the topmost node, which gives you a summation and then converts it to a percentage. And that percentage value indicates how close the input value matches the pattern that the graph was trained for. And so for A, we would go through the same process as the 3-color process. We would give it each pixel, we'd feed it into the network, we would see what the output is, and then we would feed it B and say this is a negative result. So we want the result, the output result, to be very distant from our A, and we go through each letter in the alphabet until A is separated enough from the other letters, and we have enough of a separation to be able to declare that when we see this pattern, we know it's A. When we see the other patterns, we know it's not A. And so how do we extend that into the entire alphabet? So as I was saying, we created a link weight set just for A, just to identify A as the value that we're looking for. So if I want to look for B, I'm going to have to do the exact same thing and adjust the link weights until B is isolated from the rest of the inputs. Now the benefit is I don't have to recreate the graph. I don't have to guess how many layers I'll need, because it should probably be close to what A had. Now granted, we might go through all of these and realize we need a couple more layers, but then we could probably use that same graph for each letter in the alphabet instead of having a distinct graph for each character or letter. We can have one graph with a bunch of distinct link weights, and then we can just load the link weight, do a comparison against the character, determine if it's A or not. So the process now is we have our graph, we load up the A link weight set, we run the scanned in character or letter against the network, and it says 34%. So then we load in the B link weight set. We compare the scanned in character against B, and we get 24%. And we keep doing this all the way through the alphabet until we find the character that the scanned in one matches. And then we know in an ASCII representation, or for the computer's perspective, what character this is. Instead of it just being a picture, we now have an actual value representation of the letter. It sounds like a lot of work, and it is. It's a lot of computational processing, but I want to move on from this one. But this is the complete picture, if you will, of how a neural network works. It's very simplistic in concept, but as you can see with the graph that I just drew out just for one character, these things can get really big. And imagine processing a full picture, which is the next thing I would like to discuss. We have a picture of a person. I have no idea who this person is. Found it on the internet, but it's a good representation of the process of trying to identify a picture of a person. So the first phase is to do some pre-processing of the image to get it down to just the lines. Basically adjusting contrast, adjusting a bunch of photo effects, if you will. I don't know Photoshop as well as to know which filters and which adjustments would be needed to make this absolutely happen, but basically you're going to process the image to the point where you just see the edges. Once we have that, we can then break up the image into pixel blocks, if you will, small enough processing blocks to feed into a single neural network. And so what we would do is, in this example, broken it up into 96 squares. And so we will take each square and we'll train a neural network to recognize a line going in a given direction. So we got one going at an angle to the right, we got one at an angle going to the left, we got one vertical, and we got one horizontal. Now we could probably create a bunch more examples of these lines, and we probably need to be able to truly capture all of the potential edges. But this neural network is going to work off of this for now. We're going to keep it simple. But the network now will be trained to recognize those edges distinctly. You know, same process we went through with the characters, same process we went through with the 3 color blocks. We'll feed it all the values that we have, all the edges that we have, and make sure that we can create a link weight set that uniquely identifies one of them, and then go to the next one, create a link weight set that uniquely identifies the next one, so forth and so forth. Once we have that, then we can take our blocked picture, take a block, feed it into the network, find out which link weight set it matches up, and then do that for each one. And we're going to have 96 results for the first pass. Now we need to go to the next layer, or to the next set of neural networks that will take in those 96 results, and it will determine what kind of shapes are there. Are there circles? Are there squares? Are there triangles? And then we take those results and we feed it into the final network. In this case, we can make it more complex or try and keep it simple. It depends upon the the picture and the type of person we're trying to match it against. But we then have, in our example, we're going to just have 3 sets of neural networks. In the third network, we're going to take those shapes, and based on the shapes we have, we will say that this is person A or person B. In our case, this is Becky. I have no idea if that's her real name, but name that popped in my head, so that's who it is. And so that last neural network, I mean, again, we're doing the same thing for each layer. The shapes layer will have a set of link weights for each shape, and it'll you know, however many shapes we end up having in the picture, it will actually, so thinking about this, we want to probably do, so we have our single blocks, and then we'll probably do a group of blocks, so 2 by 2. So that'll be the next layer, which will start to identify, are they still line shapes or are they, you know, squares, circles? And then we'll do a 3 by 3 grouping, and then we'll have the 2 by 2, and then we'll take probably another 2 by 2 of the 2 by 2s. So it'll technically be a 4 by 4 grid of the picture, but now we've bubbled it up from the neural network. So we took 4 of the neural network results on the first layer and bubbled it into 1 result in the second layer. And that 1 result may represent just a line, it may represent a shape. And then we bubble that up into the next layer, and we can say that 4 neural networks from the previous layer could potentially equal a shape. We might be getting to a point where we see shapes, and we keep doing that until we get to the top most layer, where we have all the shapes calculated and percentages applied to it. And then that final one will do a comparison against what it knows, and it'll say, oh, well, I know who Becky is. I've been trained to recognize her shapes, and so therefore I believe this is a picture of Becky. And again, we have to train each layer to recognize the specific patterns coming through on this picture. Now, how does this work if we just move the picture 5 degrees to the left, or 5 pixels to the left? How's that gonna, that's gonna impact it greatly. Now, granted, there are training approaches where they do, you know, pixel shifting, and they'll retrain the network, and they'll say all of these shifted images are the same picture, so train yourself to be able to know that these pictures are all the same, you know, adjust the link weights. And so now you can then feed it like a male person, another female person, and start to see if the results are separate enough. Again, back to the same issue. Are we getting distinct values every time we see a different picture, or a different picture of a person? Because we just trained it to recognize variations of the same picture, so now we want to be able to make sure that even though it sees the variations, can we make sure that these images of different people are actually recognized as different people? And so then we'll retrain the graph again to make sure that they're distinct. Now, as I discussed the steps, these layers of neural networks, that's actually how deep learning works again. Actual or current or older approaches to this each layer that I discussed, finding the edges, finding the shapes, that's actually currently being used, or the approach that's currently being used is algorithms that are custom made for solving that specific problem. Trying to identify an edge, that's like graph theory, where you're trying to calculate an equation that approximates a line. So they're using techniques like that all the way through to the last step, where it says, well, now that I've calculated all this stuff, feed these results into a neural network, and then those results then are compared to known images of people, and you then try and separate out the results to make sure that our link weights are saying that the picture of Becky is 94% versus the picture of John is 28%, and so forth. So by replacing all those intermediate steps with neural networks, that's the process of deep learning, or that's the approach of deep learning. So that's pretty much all of it. Neural networks aren't as complicated from a high-level view. I mean, it's a lot of work to build these things. You have to, you have to have a large data set. You have to, identify what values or which ones you're looking for versus which ones you're not looking for. And you have to sit there and go through the training process. And even, at this level of doing every layer as a neural network instead of using algorithms at those layers, that's even more work that you have to sit here and train and make sure that these things are doing the right or giving the right results that you're expecting. So with that complexity takes a lot of time to and a lot of processing power to create these results. So I want to reiterate these last. I have two more slides, and they're basically I discussed these topics on the NLP conversation, but these things still require human knowledge. As I discussed, you identify the pattern as a person, and then you work through the process of training that neural network to be able to separate out negatives versus the positives, the things you want to recognize versus the things you don't want to recognize. But then again, you're still limited to a specific domain, or in this case, an image. So a domain with regards to an image, you're looking at a person's face, or you're looking at a vehicle, or you're looking at an animal. Those are different domains because the shapes that could be recognized are going to be different. You're going to see a lot of different patterns between those. Could you potentially build a neural network that's big enough that can handle the different domains? Yeah. Can you create a computer farm that's capable of processing such a large neural network? Maybe. Which goes back to the last point, computationally intensive. These things, the more you try to recognize, the bigger these networks get. And that's a that's a hard problem to solve. Breaking it down, they're doing a very simple processing task. Well, so neural networks are designed to solve any problem because they're connected to every node is connected to every node kind of approach. Well, given two layers, every node is connected to every node, and then the next layer, every node is connected to every node. Taking that approach, they're trying to say that this graph can solve anything that it's presented with. It's an answer to everything, versus trying to find an algorithm that can answer what it's seen before. Let's say it that way. So if you have an algorithm that can just answer what it's seen before, then you don't have as much connectivity going on. You don't have as much processing going on. It's a lot less computationally intensive. But how do we get there? That's reserved for another conversation, I guess. And then, of course, where do we go? Talking about how do we create an algorithm that doesn't have as many connections? How can it, the first step would be for it to learn on its own, creating those nodes instead of having all the possibilities in its capacity. Only create nodes as it needs them. And then, with all these learning abilities of this algorithm, hopefully it'll be able to adapt to other domains or grow exponentially as it sees more and more information. And then, of course, how does it respond to changes in its domain? Again, if it's adapting, if it's learning, if it's actually learning, as we discussed in the neural network isn't actually learning. You're just adjusting link weights to shift the graph from one perspective to another. And in doing so, you're still only forcing the graph to recognize one thing as opposed to multiple things. Versus a different approach where you have a graph that can grow, not only grow itself with nodes, new nodes and new links, but also those new nodes represent new concepts, so it can recognize more than one thing if we were able to figure out that approach. And that's where I'm going to leave it. So this is a brief overview, or a long overview, of neural networks and how they work, and some potential concerns with how they work. That's all I got. So I hope you learned something. If you like this video, of course, click the like button. Comments, complaints, corrections in the comments down below, that'd be great. Till the next video. Thanks for watching.